This problem is the last problem from your homework assignment, and it's a pretty complicated one. In it we have Pierre, who is jumping onto the counter of his kitchen from the ground. And there's some information here that could be considered, I suppose, a little bit confusing. One is that he has to get onto the counter, which is 1 meters high. But because he, first of all, has some height, and he's able to bend his legs and so on and so forth, he's able to actually get onto the 1 meter high counter by simply raising his center of mass by 0.6 meters. And that's what I illustrated here with this 0.6 meters. And then you're also told that he's 0.5, that's a 0.5 right there, meters away from the counter. So he's moving 0.5 meters forward and 0.6 meters up. And he's just barely able to make it. That's our just barely. So we can assume that he gets up here when his vertical velocity at that point is 0. This is going to be his maximum height. After that point, if it were to continue, you would start to see, a decline in terms of his center of mass if the counter wasn't getting in the way. But that's not what's happening. He gets onto the counter, and that's the point where he hits his maximum height, and so a vertical velocity of 0. And what I'm going to do is I'm going to go through and try to list as many givens as I can here. So we'll start with the horizontal, and that one's pretty easy. At least at the start, we have our initial and our final positions at 0 and 0.5. And the velocity stays constant since there's no horizontal forces acting on the person. The problem is that we're never told how fast he's moving. We're just told that he's launching himself upwards at some velocity and at some angle. And it's this angle that we're ultimately trying to find the angle at which the initial velocity was directed. But that leaves us with two unknowns, just in this little formula here. And we don't know time. We're not sure how long this guy is in the air. So that's it for the horizontal direction, and so far it doesn't look too promising. We have ultimately here, I'll underline it a little differently, 3 unknowns. And if we recall, we only have the one equation. So I have velocity in the x equals delta x divided by time. And the only reason that this is our only equation is because the acceleration is 0. There's no forces for us to use to try to figure out what's going on. It's all based on this one. And I can do a little bit of substitution here if I would like. Initial velocity times the cosine of theta equals delta x over t. But I'm at a bit of a loss as to what to solve for. So I'm just going to leave it go at that for now. Then we look in the vertical direction. And in the vertical direction, the initial position is 0. The final position is 0.6 meters, because we're basing this off of the center of mass, not the actual height of the table. And obviously this guy will eventually stand up, but he'll be using the force of the countertop to lift his center of mass upwards, not just the initial launch. And the initial vertical velocity is going to be the overall initial velocity times the sine of the angle. And as I stated before, the final velocity in the y direction is just going to be 0 because we've gotten to the maximum height. That's it. The acceleration we know, negative 9.8 meters per second squared. And time. We once again don't know time. And this is ever so slightly more promising. We still have 3 unknowns. They're the same 3 unknowns, which is a little bit promising. That at least means that we're not introducing any more new unknowns. And also we have some more variables to work with here. The difficulty, I think, is how do we handle this? How do we get through this based on what we know? And there's actually no way for us to effectively solve for the time other than based on this height and that initial velocity. So one thing that we could do is, if we wanted to solve for the time, we could actually kind of go backwards in time. We could say, you know what, this guy's starting off with an initial vertical velocity of 0, and he's going to wind up with some unknown velocity as he gets back here. That exact velocity isn't really important. because he's got to go up enough to get up here, and this is the maximum height that he reaches. So what I mean by this is that I could transform, if I would like to, I can transform this into a slightly different problem, a backwards in time problem. And what that would look like is, I'll do vertical prime, just backwards in time. So the initial height here would be 0.6, the final would be 0, the initial velocity in the y would be 0, the final velocity in the y we don't know, the acceleration negative 9.8, and the time we don't know. And what we could do here is we have that no v equation. So if we don't know what v is, we could solve for t if we want to. Okay? So that's one option that's available to us. And it's a pretty straightforward, easy option to take if we want to. So I'll just go ahead and say y equals y naught plus v naught yt plus 1/2 at squared. And this whole term goes away. And this whole term goes away. And we're left with 0 equals y naught plus 1/2 at squared. And I can just rearrange this and solve for the time. So I get the time is equal to the square root of minus 2y naught divided by a. Okay, at this point it starts to get a little bit tricky. So let me just quickly write down what the answer to this is. So if I put in the 2 and then the 0.6 and then my acceleration, I wind up with about 0.35 seconds. Okay, so that's the first major obstacle. We got one of our unknowns squared away, and we know how long the person is going to be in the air. Now what we need to do is go in a little bit deeper. So I'm going to go back to this first vertical setup here, and I'm going to make use of the fact that I now have the time, and I know the initial and the final velocities, and the positions. And I'm going to do that by doing actually the no t equation. I already found time, and I'm going to make use of it up here, but I think that it might be easiest for me to continue on by using vy squared equals v naught y squared plus 2a delta y. And this vy, 0. So now I have the opposite of v naught squared sine squared theta equals the opposite of 2gy. And this opposite came about because this is actually equal to negative g. And the negatives cancel out, and I'm able to then solve for the sine of the angle. And normally I recommend that you solve for the unknown that you don't know and you don't care about. I usually recommend solving for that first, but in this case we'll solve for the sine of the angle first, and then hopefully you'll see why in just a moment. So I'll have the square root of 2gy divided by the initial velocity. Now what I can do here, and this is where it gets a little bit interesting, I think, is that we can kind of redraw a triangle. So I'm going to redraw my triangle, and I'm just going to use the sine of the angle as my guide for what goes on each side. So sine is opposite over hypotenuse. So my hypotenuse is just v naught. The opposite side is the square root of 2gy. And that means that this adjacent side is the square root of the hypotenuse squared minus the adjacent side squared, which is just 2gy. We square the that does not look like a very good y. If we square the square root, it goes away, and we have it under the new square root. So I square this, I get 2gy, and my adjacent side then is v naught squared minus 2gy. What this allows us to do is construct a cosine formula. So the cosine formula, cosine theta, is going to be equal to the adjacent side, v naught squared minus 2gy, divided by the hypotenuse, which is v naught. And what I'm going to do is I'm going to stop this video for now, and we're going to continue on in a new video.